So as I mentioned at the beginning, that question that Eli and Ricky wanted to solve, and as a matter of fact, Erdős and Klein and Szekeres and many others wanted to solve, remained even asymptotically open for a long time, more than 50 years, and finally it was Andrew who found a crack on it, and it is related to all kinds of other interesting questions, and he will talk about some of them related to topological graphs. So thanks, Andrew.
Okay, so thank you for letting me speak on DCG Day. So I have many fond memories talking to Eli and Ricky back when I was a graduate student at NYU. At that time, I worked on a lot of problems in graph drawing. So I thought today that I would share some of the recent problems and results that I've been thinking about in this area. Kind of more specifically, Ramsey-type problems on in graph drawing. So actually, when I was a graduate student at NYU, one of the very first papers I read, and perhaps one of the most influential papers in my research career, is perhaps this paper here by Ricky and his co-authors, where they showed that if you do draw a graph in the plane, and there's no three pairwise crossing edges, and if the drawing is what's called simple, then the number of edges is at most linear in the number of vertices. So today, graphs drawn in the plane are frequently called topological graphs. So just to be clear, a topological graph is a graph where your vertices are points in the plane, and then the edges are curves connecting the corresponding points. And so we all know by Euler's theorem that if you do have an n-vertex topological graph with no crossing edges, then the maximum number of edges in this graph is at most 3n minus 6. So in particular, if your graph is planar, then the number of edges is at most linear in the number of vertices. And then we say that a topological graph is k quasi-planar if there's no k pairwise crossing edges. And so when k is fixed, so for example, if k is, let's say 3 or 4, there's this very old famous conjecture that states that every n-vertex k quasi-planar graph has at most big O of n number of edges. So the number of edges is still at most linear in the number of vertices. This conjecture is still open in general. Kind of the first result towards this conjecture was that earlier paper I mentioned 2 slides ago by Agarwal, Arnav, Pach, Polak, and Sharir, where they proved the conjecture when k equals 3, but they also had this simple condition that I'll talk about later. Without the simple condition, this was proved by Pach, Radojcic, and Toth in 2003. And then it was reproved by Ackerman and Tardos in 2007 with a better constant in front of the n. And then the case when k equals 4 was solved by Ackerman in 2009. But for larger values of k, it's still not known whether or not the number of edges in a k quasi-planar graph is linear or not. So the best upper bound for k at least 5 is this quantity here due to Fox, Bach, and myself. And so when k is fixed, there's basically an upper bound that is n polylog n. So this conjecture has been open for quite some time, and there's many variations of this conjecture. As I said before, there could be this simple condition. So I won't go through all of these variations, but I will mention one more result that I thought was quite nice, which is that if you insist that the edges are drawn with straight line segments, then every such k quasi-planar graph will have at most n log n number of edges. And this was shown by Walter in 97. So in my talk, I'm going to focus on kind of the dense setting. In particular, I'm going to focus on the complete topological graph. So one, I guess, corollary of this result here, if you just set it equal to n squared, you get that every complete n-vertex topological graph contains n to the epsilon, where epsilon's an absolute constant, pairwise crossing edges. So complete n-vertex topological graphs have this kind of large, nice structure inside of there. And so kind of the basic question I've been thinking about lately is what other large patterns can you find in complete topological graphs? Kind of more specifically, the patterns that I'm interested in are planar, or they're non-crossing. And because I'm interested in non-crossing structures, you're going to have add some condition to these topological graphs, because you can easily draw any complete topological graph with every pair of edges crossing. So for example, you could just place your vertices down here, pick a point somewhere in the plane, draw all your edges through that point, and then this complete topological graph will have every pair of edges cross. And so therefore, there wouldn't be any large planar structure inside of here. So in order to kind of, avoid this, this situation, we'll add this simple condition. So a simple topological graph is a topological graph where now you insist that every pair of edges have at most one point in common. And so for the rest of this talk, I'll just be focusing on these types of graphs, simple topological graphs. In simple topological graphs, every pair of edges essentially looks like one of these three pictures here. So maybe two edges share a common endpoint, and that would be the only point they have in common. Or they have a common interior point, in which case we say that these two edges are crossing, or they just simply have no points in common. And so we say that these two edges are disjoint. So now, given a complete simple topological graph, I want to ask the same type of question. What kind of large, I guess, natural patterns can you find inside of here? In order to make this a little bit more precise, I need one more definition. So it's this weak isomorphism between two topological graphs. So we say that topological graphs G and H are weakly isomorphic if there's an incidence preserving bijection between G and H such that two edges in G cross exactly when the corresponding edges in H cross. So now with this notion of weak isomorphism, when I look at the complete simple topological graph, what kind of large pattern up to weak isomorphism can I find inside of here? At least to me, probably the most natural thing, the most natural topological graph one can think of is probably the complete convex geometric graph, or just simply complete convex graph. And I'll denote this by this C sub M here. So this is just simply a drawing where you place your vertices in convex position, and then you draw all your edges with straight line segments. This is quite a natural way to draw a graph, I think, and it's I guess it's pleasing to look at, but it also has a nice combinatorial description, which is that you can order the vertices V1 through Vm such that two edges, let's say Vi, Vj, and Vk, Vl, these two edges cross exactly when the interval Ij and Kl intersect, but they're not nested. So in other words, when I is less than k is less than j is less than l, or when k is less than I is less than L is less than j. Okay, so given that this is such a natural, I guess, looking graph, is it true that if you have a sufficiently large, complete, simple topological graph, will it contain a large convex geometric graph, complete convex geometric graph inside of there, up to weak isomorphism? Or more specifically, would it even contain a C5? So this thing here. And kind of interestingly, the answer is no. The reason why the answer is no is because of the following way you can draw the complete simple topological graph, which is basically this picture here where you draw it in like a twisted way. So this here I'll call the twisted complete graph and denote it by this T sub m. So you basically draw your edges in this kind of twisted way here. And it's not maybe so pleasant to look at, but actually this thing too has a nice combinatorial description, which is that you can order the vertices V1 through Vm, kind of like these vertices down here. And in this twisted complete graph, two edges, Vi, Vj, and Vk, Vl, these two edges will cross exactly when the interval ij and kl are nested. So in other words, when I is less than k is less than l is less than j, or when k is less than I is less than j is less than l. So maybe it's a little hard to see it in this picture, but if you notice the edge 3, 4 and the edge 2, 5, because the interval 3, 4 and 2, 5 are nested in this ordering, these two edges here are crossing. And that's exactly when two edges cross in this complete twisted graph. Okay, and so it was observed or proved by Harborth and Mangerson back in 1992 that this complete twisted graph, TM, will not contain a subgraph weakly isomorphic to C5, this complete convex geometric graph. And it's not so hard to see why. So for sake of contradiction, suppose you have these 5 vertices in the complete twisted graph on m vertices, such that these edges here, there's this weak isomorphism with this picture here. So this C5, this complete convex geometric graph on 5 vertices, it has these 5 special edges out here, this 5 cycle. And each red edge here does not cross any of the other 9 edges in this complete graph here. And so if I look at this 5 cycle, that means 4 of the edges are going to be incident to the first and last vertex in this ordering here. So F3 and F5. But since there's 5 red edges, one of the red edges must be completely inside of here. So let's say F4 and F2. And we know this edge is drawn in this kind of twisted way, but then that means that it crosses F3, F5 because, you know, this interval here is nested with this interval here, which means that this red edge does not have the property that it does not cross all of the other edges. And so therefore we get a contradiction, and therefore there's no way that this thing will have a C5 inside of there. Okay, so you can avoid a C5 in a large, complete, simple topological graph, but it was shown by Pach-Solymosi-Toth in 2003 that you can't avoid both C5 and T5. So more specifically, they showed that every complete simple topological graph on n vertices contains a topological subgraph on m vertices, where m is roughly log n to the 1/8. That's weakly isomorphic to Cm or Tm. And so what I plan to do towards the end of my talk, after I talk about some more nice problems in this area, I plan to roughly sketch a proof on how you can improve this bound, which is joint work with my student Ji Zeng, to roughly log n to the 1/4. Or at least I'll just provide some key ingredients on how you can get this improvement. But in the other direction, unfortunately, we weren't able to come up with any non-trivial constructions. So in the other direction, you can get a log n bound just by placing your vertices on the real line, let's say. And then for each pair, you uniformly at random draw a half circle, either above the x-axis or below the x-axis. And then if you just apply the probabilistic method, you can show that there is a drawing, or there is a complete n-vertex simple topological graph that does not contain a topological subgraph on roughly log n vertices that's weakly isomorphic to Cm or Tm. Apart from this construction, which gives log n, we're not aware of anything better or closer to this log n to the 1/4. Okay. But before I talk about this, I wanted to kind of mention some other nice problems in this area. So one, I guess, application you get from this result is that once you do obtain a Cm or a Tm, then it's not hard to find a non-crossing path among these edges here and these edges here. So in other words, if you just take our result, you can conclude that every complete simple topological graph on n vertices contains roughly log n to the 1/4 vertices. That's a non-crossing path. And we were able to slightly improve this to roughly log n. But we think it's quite a nice question to see whether or not this is polynomial or logarithmic. So in fact, we conjecture that it should be polynomial. So we conjecture that there is an absolute constant epsilon, such that every complete n-vertex simple topological graph contains a non-crossing path on roughly n to the epsilon vertices. The reason why we made this conjecture is because we know it's true for disjoint edges or pairwise disjoint edges. So we know that in the complete n-vertex simple topological graph, you can find a polynomial subset of edges that's pairwise disjoint. So this was shown by myself, Fulick, and Ruiz-Vargas. And in particular, Ruiz-Vargas showed that you can find roughly square root n edges that are pairwise disjoint in the complete simple topological graph. But whether or not you can kind of connect them and make this non-crossing path, this appeared to be quite non-trivial to us. And so we thought that this was quite a nice problem. Okay, and then more fundamentally, we were curious whether or not in the complete simple topological graph, whether or not you can find an edge that simply crosses very few other edges in order to kind of construct this non-crossing path. On average, each edge will cross about n squared other edges. But you know, we're hoping that we can find like a special edge that crosses very, very few other edges. And so if we let h of n be the smallest integer such that every complete n-vertex simple topological graph contains an edge that crosses at most h other edges. It was shown by Valtar that this is at least n to the 3 halves. So in other words, he constructed a complete simple topological graph in which every edge crosses at least n to the 3/2 other edges. And then in the other direction, Kinshall and Valtar showed that this is at most little o n squared. So I guess at most n squared over log n to the 1/4. So you can find an edge that crosses very few other edges. Their proof was actually based on that old result of Pach-Solymosi-Toth, an asymmetric version of it. And so if you just simply apply an asymmetric version of this result, and if you just follow their arguments using this result instead, then you can slightly improve this upper bound here to roughly n squared over square root of log n. But we conjecture that you should be able to find kind of an edge that crosses even fewer edges. We conjecture that you could find an edge that crosses at most n to the 2 minus epsilon other edges, but unfortunately we weren't able to show this. But we thought that this was a very nice problem that we couldn't solve. Okay, so what I wanted to do in the last 5-10 minutes or so in my talk is just to give a sketch of the proof of this, just to give you some ideas on what kind of ingredients goes into the proof. I won't really say much about the proof other than highlighting the key ingredients. So suppose you have this complete simple topological graph, which I called Kn, drawn in the plane. You can assume that there's a vertex on the unbounded face because you can always just project your drawing onto a sphere and then pick a face with a vertex on it and then project that drawing back so that that face becomes the unbounded region. And then this new drawing, I guess, would be weakly isomorphic to the old one. And then if you look at the edges emanating out of this fixed vertex, you have this star picture because it's a simple topological graph. They all have this point V0 in common already. And so therefore you can order the vertices based on how the edges are emanating out of V0. And because V0 is on the unbounded face, you know that there's no edge that's going like wrapping around in this direction. The edges are kind of, wrapping around in this direction here. And so we followed the argument of Pach-Solymosi-Toth, where they looked at these vertices up here, the endpoints of these edges emanating out of V0. And they observed that if you look at any triple, Vi, Vj, and Vk, every triple Vi, Vj, Vk will have one of 4 configurations. One way of thinking about this is every time you pick a triple and V0, you'll have a picture of K4, and there's basically 4 ways of drawing a K4 in a simple way. And so these are the 4 configurations you can have of this triple Vi, Vj, Vk, and they labeled it 0, 0, 0, 0, 1, 0, 1, 0, 0, and 0, 0, 1. Basically, the 0, 0, 0 pattern is the planar K4. The 0, 1, 0 pattern is where this middle edge emanating out of V0 is getting crossed. The 1, 0, 0 picture is where this left edge emanating out of V0 is getting crossed. And then the 0, 0, 1 picture is where this edge here is getting crossed. And so what they showed is that now based on this color pattern on the triples with these 4 colors, now the goal is to just simply find a monochromatic clique with respect to one of these color classes. So for example, if you find m vertices such that every triple has this color 0, 1, 0, then it's not hard to see that those m vertices would be weakly isomorphic to the complete convex geometric graph. And likewise, if you have m vertices such that every triple has this 1, 0, 0 pattern, then what you would end up with is m vertices that's weakly isomorphic to the complete twisted graph. So now you have this, I guess, hypergraph Ramsey-type problem. And so here's where I skip a lot of the arguments, but roughly some of the key ideas that they use is they apply this Erdos-Rado-Greedy argument. And then they also apply the Erdos-Zekresh monotone subsequence theorem. And then they piece everything together and also make some very nice topological arguments. And this is roughly how they get this log n to the 1/8. So me and my student Ji Zeng, we made basically 2 observations, and then we kind of pieced everything together in a nice way. The first observation was quite simple, which is that for 2 of the color classes, 1, 0, 0 and 0, 0, 1, these color classes are transitive, meaning that if I look at any 4 tuple, Vi, Vj, Vk, and Vl, if you know that this triple, Vi, Vj, Vk, has the 0, 0, 1 pattern, and if you know that Vj, Vk, Vl has the 0, 0, 1 pattern, which means that this edge here has to cross this edge here, then you get a picture that roughly looks like this. And essentially, it's not hard to conclude that just based on those 2 pieces of information, every triple among these 4 vertices must have the 0, 0, 1 pattern. And the same thing would be true for the 1, 0, 0 pattern. And so now, rather than trying to find m vertices such that every triple has the 0, 0, 1 pattern, if you can find what's called a monotone path instead, meaning that if you can just conclude that this triple has the 0, 0, 1 pattern, this triple has the 0, 0, 1 pattern, and likewise all of these triples, then because of the transitivity, that's enough to conclude that every triple among these m vertices has the 0, 0, 1 pattern. And so therefore, then you would have something that's weakly isomorphic to the complete twisted graph. So it turns out that these 2 color classes here are transitive, which is quite nice, which helps a lot. And then it turns out that these are not transitive. So something more has to be done. But just even if you stopped here, even just by observing that these 2 color classes are transitive, you can improve the bound to roughly log n to the 1/6. And then the second observation that we made was that instead of using this greedy argument process, we use a technique from online Ramsey theory, which is based on this game between builder and painter. So in a nutshell, this old argument, you keep pigeonholing for every edge and vertex you look at in this complete graph. And in this online Ramsey theory, you only pigeonhole certain edges and vertices. So it's a lot more, you pigeonhole less, and you do this a lot more efficiently. And so combining these 2 ingredients, this is roughly how you get this log n to the 1/4. And I think that's, and then you have to piece everything together, but I think that's all I'll say about this proof. Okay, and so just a few concluding remarks. Like I said, I think it would be quite interesting if there was a non-trivial construction. So a construction of an n-vertex simple topological graph that doesn't have little o log n vertices, that's weakly isomorphic to CM or TM. And also those two problems I mentioned earlier about kind of the difference between logarithmic and polynomial, whether or not you can find a non-crossing path on n to the epsilon vertices, or whether or not you can find a very special edge that crosses very few other edges. We thought that these were also two quite nice problems in this area. So, and I think that's it. So thank you.